Okay, so in this video we're going to be looking at 5.2. So we're going to start with two questions of things that we have worked with before. First question is, what is a bisector? Well, this showed up a bunch in our proofs. Bisector is anything that cuts something in half. So a segment bisector would be a line, ray, or segment that intersects a segment at its midpoint. It's anything that cuts through the midpoint. And the way you know it's a midpoint is because you get congruent sides here and here. Well, a perpendicular bisector would just be one of these lines that bisects a segment that is, you guessed it, perpendicular to that segment. So maybe something that looks more like this, where we're told explicitly, hey, this is a bisector, and hey, this is also perpendicular to that segment. So that's what we're working with today. What we get from this perpendicular bisector is the following theorem, and that is not only are AP and BD the same length, but also if CP is the perpendicular bisector, any point on the line CP is equal in distance to the two endpoints of the segment. So for sure, C to A is the same length as C to B. But you could put a point anywhere on this. So if you put a point even like here, PB would be the same as PA, or you could put a point down here, or you could extend it even further down. From this point to B, it's the same distance from this point to A. You essentially get kind of a kite-looking thing with this perpendicular line. The converse of this is also true. So if your segments are equal in length, then you can say for sure that point C in this case is on the perpendicular bisector. So what that allows us to do is stuff like this. Given that BD is a perpendicular bisector of CA, or AC, it's a bisector and it's perpendicular, find the length of AD. Well, AD has to be the same length as CD based on what we just saw. So at this point, we can just play the algebra, subtract 3x. So x is 7. Now, AD is not 7, just x is 7. So AD, you just plug the 7 in, you get 35. So AD is 35. If you'd like to pause the video now and try this one, you sure can. Otherwise, I'm just going to burn right through it. JK is on the perpendicular bisector of NL. Find NK. Basically, we're doing the same game as we did in the last problem. Set those lengths equal to each other. Play the algebra. So I'll subtract 2x, or excuse me, subtract 4x. Add 5. X is 3. So if x is 3, I plug that in to find NK. 6 times 3 is 18. 18 take away 5 is 13. So NK is 13. So our main application of this is actually going to be with a full triangle. So here I have a triangle. We'll call it ABC. ABC has 3 segments, obviously, that make a triangle because a triangle has 3 sides. So what I did for each segment is I created a perpendicular bisector. So FA is the same length as FC. So FP is a perpendicular bisector here. AD and DB are the same length, and then DP would be the perpendicular thing that cuts that in half. And same thing with PE here. So this not only tells us that FC is congruent to FA, DA is congruent to DB, BE is congruent to EC, we also get more from this. So if we just take this one corner at a time, if you will, or one side at a time, let's just look at this perpendicular bisector here. If we ignore everything on the left and on the bottom, if PE is a perpendicular bisector, that means any point on PE is the same distance to the endpoints of the segment. So I could put a point here, and I could say that distance to B is the same as that distance to C. That's our theorem that we just learned. So what we can do with that is we can now say this point is the same distance to B as it is to C for that same reason. And now if we look at the bottom perpendicular bisector, PC has to be the same length as PA. And PB would have to be the same as PA. We already have that marked in, but if you ignored everything else down here, like for example, if you ignore, well, that's not going to work, but if you ignore everything down here, you just have our one simple situation that we were having no problem with before. So the perpendicular bisectors of a triangle always intersect at one point, in this case point P. We call that point the circumcenter. And that circumcenter is equidistant or equal distance from the three vertices of the triangle. So the distance from P to B to P to A and to P to C is all the exact same. So what this means, and we're going to play around with this when I'm back at school on a program called GeoGebra. What that means is if all three of these blue lines are perpendicular bisectors, then the distance from this point to each of the corners is the same. So what you could do is you could actually make a circle with a center at point P. Maybe. Not going to be perfect, but pretty solid. That perfectly fits the triangle inside of it. You can do that regardless of whether it's a right triangle, an acute triangle, or an obtuse triangle. Where since that point is equidistant to all three corners, well, in that case, then we know you'd be able to form a circle because all of those side lengths would just be radiuses or radii, which is kind of cool. So as a final problem, I invite you to try this on your own. Perpendicular bisectors of ABC meet at G. Find the length of GA. This problem, there's really no math involved. It's just figuring out what you're looking at. This is a perpendicular bisector, so is this, so is this. So we know these lengths have to be the same. So GA has to just be 13, and that's all there is to it. So that does wrap us up for the notes portion of 5.2.